Hello guys, this is Mrs. Lloyd and today is Tuesday, March 24th, and we're going to talk gas exchange today. My friend I have today in the office with me is Rufus. He's a little bit too big to fit in the chair, but he tends to be a little vocal, so you might hear him kind of whining a little bit while we go through these notes. So we have with us today the gas exchange lesson. It's a little bit more complicated than some of the things we've already gone over. So you'll notice in Plan Book that I included 2 other videos at the end of this that I want you to watch. This is going to be a little bit longer, but that information will help solidify a lot of this and also show a lot of this stuff in action, things that I can't quite do on this presentation here. But we will go through the notes, make sure your study guide's getting filled out, and we'll be almost done with our notes. Your test is going to be Friday this week, March 27th. So make sure you are getting ready and prepared for that. So we are on the back side, page 10. We're going to finish filling out the pieces we didn't get to yesterday, but we talked about the events of respiration. So pulmonary ventilation is basically just breathing. External respiration, we will hit on again today. That's how the air is getting from our alveoli into the blood capillaries of our lungs. And then internal respiration is when that blood gets dropped off anywhere in my body and it leaves the bloodstream and goes into those cells. That's internal respiration. And then we're going to focus here on gas transport and how it transports itself throughout the body. This formula here, I'm going to talk about in a second, but if you want to write it down, go ahead and put it at kind of the bottom of your study guide here, underneath the whole little tree. It really does deal with the gas transport, but it might be a little hard to fit it all in there. So a few things, well, I'll come back to this formula in a minute. You can pause the video if you want to, or jot it down as I'm talking here. So if you haven't already, I want you to write O2 and CO2 on our 2 branches of the gas transport. We're going to talk about how, when it's in the bloodstream, what is the gases attached to, or what form is it in as it's traveling about. Oxygen, O2, is mostly attached to our red blood cells in hemoglobin, but about 2% of it, maybe even a little bit less, like 1.5%, is dissolved in the plasma as just oxygen. So there is some gas dissolved into the liquid of our plasma, mostly water. So there's some oxygen in there, but not very much. About 2% of the oxygen we take in goes into the plasma just as dissolved oxygen. The rest of it, about 98% of it, binds to hemoglobin in our red blood cells. And hemoglobin is a molecule, a protein molecule that's in our red blood cells. And for every 1 hemoglobin, I believe it can hold 4 oxygens. And there's lots of hemoglobin in your red blood cells, so it can attach to many of these. When it does bind to hemoglobin, we don't call it oxygen anymore. We call it oxyhemoglobin, just a signal that it's oxygen stuck to this protein hemoglobin. So oxyhemoglobin is when it's attached. Most of the blood traveling around my bloodstream is attached that way to the hemoglobin molecule. Carbon dioxide is a little bit different. About 7% of it is dissolved in the plasma itself. And we don't normally talk about this when we talk about red blood cells. It transports oxygen. Yes, it also transports carbon dioxide. Carbon dioxide will also bind to hemoglobin. When oxygen gets dropped off, it will pick up about a quarter of the carbon dioxide, ends up in your red blood cells attached to hemoglobin. So that process does happen opposite, just not in the high amounts that it does as it's transferring around the body. One of the second video, the crash course video from today, is going to go over that, and you can visualize what that looks like. But the majority of carbon dioxide isn't just plain carbon dioxide in your plasma. It turns into bicarbonate. So the majority of carbon dioxide, 70% of it, when it dissolves in the plasma, it doesn't stay as straight carbon dioxide. Instead, it turns into bicarbonate molecule, which is abbreviated HCO3 with a little negative sign because it's missing or it's gained an electron. So that's what the formula is that I had you write down. So when the carbon dioxide goes into the plasma, which has tons of water in it, we know plasma has lots and lots of water, it turns into an acid. Now, carbonic acid is not good for my body. I don't want my blood to become too acidic. That's a bad thing. So it then immediately strips the hydrogen ion off and turns into bicarbonate ion, which is a much more safe version for it to be transferring and hanging out in my bloodstream as. And so that formula happens the second, when most of your carbon dioxide dissolves into the plasma. Some of it stays as carbon dioxide, 7%, as we wrote down, but most of it goes through this chemical formula and changes to bicarbonate. We're going to talk more about this on another labeling that we're going to do. All right, so now we are moving over to some pictures we saw yesterday, I think, or maybe it's 2 days ago. This is page 4 of your notes. We are going to zoom in and talk about what is happening in these alveoli of our lungs for gas exchange to occur. This picture is from your textbook. I really like this picture because you can see how much those capillaries saturate those alveoli and really surround each of those air sacs, which is where the gas exchange is going to happen. So we're here on page 4. You guys have this picture in your study guide. I'm not going to label everything on here because you don't need to know all these label lines. If that bugs you and you want every single thing filled out, it's on page 819. I think I also have it on the next slide of the PowerPoint here. But there are a few important things I do want you to label. And if you are, I'm going to label everything kind of person, maybe highlight these things. So first of all, we are looking at the sacs of the lungs, those alveoli. So that's what each of these are. This is the internal view of those sacs. I want you to notice here what type of cell tissue we are looking at. So if we have this top view of the cells, like we do right here and here and here, they kind of look like little pancakes or discs. And then they sort of curve over. This is a 3-dimensional structure. And these have a single cell squished structure. Remember what type of tissue was one cell thick and squished? Simple squamous epithelial. So these are our simple squamous epithelial tissue that lines the sacs of the lungs. And this is super duper important because as we talk about the gas exchange that occurs here, it's only one cell thick. So all of these are simple squamous epithelial, except for some of these notable structures. All of the things that are red on here are representing the blood capillaries. The picture I just showed you surrounding all of the alveoli, those are those blood capillaries that are like hugging tight on the outside of each of these. This is where the gas exchange happens. And so this is important because we're talking about air leaving these sacs and going into the blood right there. A few other things to note on here are those green structures. I don't know if they're actually really green in real life, but they are important because they are cells that make surfactant. And surfactant is this type of lipid molecule that prevents the alveoli from sticking together and collapsing. So this is a sac that has to stay open. And as you inhale and exhale air constantly throughout your day, the pressure is changing inside those sacs. If every time the air left those sacs and they just totally closed and collapsed, it'd be very hard to reinflate them. Remember, if you've ever blown up a balloon, it's really hard to get that balloon started. But once you've got a little bit of air in it, it's really easy to keep it inflated. That's kind of how these air sacs are. So we don't want them to collapse on themselves. And so this substance that is produced by these cells, surfactant, prevents them from collapsing and sticking together. On a little side note, babies, when they are born premature, this is one of the last things to develop in utero. They might not be producing surfactant on their lungs. And so one big concern or risk for brand new little preemie babies is their lungs and if they're working properly. And so they have to make sort of an artificial surfactant to keep their lungs functioning. Okay, the other special cell I want you guys to note is a macrophage. Those are the purple guys that are on here. They eat debris in the lungs. So if you are inhaling foreign particles, smoke, from cigarettes or vaping, or just like, let's say, campfire smoke, or like during fire season, smoke in the air, or even like you choke or like get in your lungs like a little piece of food or something. It wasn't enough to like choke on, right, and block your airway, but it went down the wrong tube. Where does it go, right? If your little cilia, if it's too big for the cilia to sweep out and for you to cough out, these little macrophages are going to eat any debris that end up in your lungs. And so they are super important for keeping it clean and clear inside those sacs, because all we want is air in there so that we can transport our gases. And that's the last label you're going to add here is oxygen going from the air sac, which is the beige part of the picture here, into the red part, which is our blood capillary. Oxygen goes in, carbon dioxide goes out. And the method it does this, super sweet and simple, just simple diffusion, high to low, okay? Where there is high oxygen in the air sacs of your lungs, low in the blood capillaries, oxygen goes from the lungs to the blood. Whereas carbon dioxide is high in the blood capillaries, and so through simple diffusion, it just moves from, again, high to low, but from the blood into the lungs. And then as we exhale, all that carbon dioxide leaves with the relaxing of our rib cage and our diaphragm, and we breathe out the bad stuff. And when you make the space in your lungs, you bring in the good stuff. It's as simple as simple diffusion. Those are just some of those important cells I wanted you to note. We have simple squamous epithelium surrounding all of those tissues that makes up our lungs. I want to talk more about the gas exchange. This is just the picture from your textbook. So this is page 5, the bottom picture of there for you. So yesterday we talked about the different respiratory events, and these two pictures are showing them. We have external respiration, which is happening in the lungs, where the exchange of gases is going from the capillaries into those air sacs, external respiration. And then we have internal respiration. This is when my blood gets to my big toe, let's say, and it is going to do the gas exchange there with the interstitial fluid in the cells there. So that's the two pictures. Very similar. It's just kind of opposite about what's coming in and what's going out. But this is gas exchange. So just to give you some labels to get yourself oriented, we have the air sacs, the brown stuff on the top. Those are the alveoli. We've got red blood cells in our pulmonary capillaries, pulmonary lungs, so the capillaries in my lungs surrounding those alveoli that we just saw a picture of. And then the internal respiration, when it's down at the body tissues, here's some little landmarks for us. We've got our cells pictured there at the top, the red blood cell, of course, and the systemic capillary, and those are the capillaries in my body system, systemic, everywhere in my body that's not my lungs, basically. And then the blue stuff in both pictures is interstitial fluid. So that little fluid that surrounds our cells, and it's like the space between. So here's a little picture just to remind you the difference between that pulmonary and systemic capillaries. The pulmonary capillaries are right here in this picture, right? That's what this is. And then my systemic capillary is this area right here, everywhere. It could be my elbow, my big toe, my brain, whatever, right? Is the systemic and pulmonary capillaries. All right, so let's talk external respiration first. So these arrows here are representing the gas exchange occurring. we know oxygen wants to go into the bloodstream in my lungs, right? The goal is to get it in there. So the red arrow is representing the oxygen, and it is binding to that red blood cell. And I want you to write that formula down. O2 plus HB, which is hemoglobin, and little arrow there makes HbO2, oxyhemoglobin. HbO2 is oxyhemoglobin. So when we just said 98% of the oxygen in my blood is going to be oxyhemoglobin, most of it gets attached to those red blood cells. And one of the videos is going to show that process in a little bit more detail for you. We call this the loading of oxygen. So imagine your red blood cells are like the carrier, right? Like the semi-truck, right? That's loading up all the oxygen, and it's going to drive that oxygen where it needs to go in the body. To my systemic capillaries, it's just been loaded onto the semi-truck as oxyhemoglobin, right? It's the best way to get it transported throughout the body. Now, carbon dioxide leaving is getting dropped off at the lungs, and we say this is unloading because it is leaving the bloodstream and going into my lungs. And so we use the phrase unloading. Next thing that's going to pop up, I don't want you to write down exactly as you see it, but this is the formula that we wrote down before. Now, when we talk about carbon dioxide unloading, I'm talking about this carbon dioxide right here in the formula. So what I want you guys to do in this space right here where my mouse is circling, I want you to write this formula, but I want you to write it in the reverse direction. If you know what each of those things represent, you don't need to write them underneath, especially if there's not room for them. But maybe if you're not sure what bicarbonate is or carbonic acid, maybe write that down. So this isn't the exact same picture, but it is very similar. And so you can see right here in that little space, you've got the formula here. That's what I want you to write down. So the reverse formula. So we have bicarbonate and hydrogen turning into carbonic acid, and then carbonic acid is being transferred into carbon dioxide and water. And that's the carbon dioxide that's getting unloaded into the air sacs of my lungs. Okay, so I want you to write that reverse chemical reaction in this small space here. Okay, so that is external respiration. Most oxygen is going to turn into oxyhemoglobin, and carbon dioxide gets unloaded after it's gone through this transformation from bicarbonate into just pure carbon dioxide, stripping out the water basically. Now, internal respiration. So now those semi-trucks driving my oxygen to my big toe, okay, they've reached their final destination, and it is ready to do the unloading now of those semi-trucks. So I have my oxyhemoglobin that's going to release the oxygen and turn into, it would leave the hemoglobin in the red blood cells, and that oxygen gets unloaded and it goes to the interstitial fluid and then absorbs into my cells. And from there, I am able to use that oxygen for my cells. Most notably, your mitochondria. Your mitochondria need tons of oxygen to make ATP, which makes everything else in the cell work. So it's super duper important that those red blood cells, the semi-trucks, are unloading that oxygen that we're carrying in hemoglobin. Carbon dioxide is a waste product that my cells are producing. And so my carbon dioxide needs to get loaded into my bloodstream, my systemic capillaries. And so it does this by the way of this same formula. Just like you did on the other half of the screen, I want you to take this formula and write it kind of tiny right here. Again, you don't have to label everything if you know what these symbols represent. This one will go in this order because when carbon dioxide enters in my capillary, just as loose carbon dioxide, it's going to bond with water and turn into an acid. My body does not want it as an acid because that will raise my pH of my bloodstream, and I might undergo acidosis. Bad things happen if your blood becomes too acidic. So my body then strips the hydrogens off and turns it into a less harmful form, bicarbonate ions. And about 70% of the carbon dioxide in the bloodstream is going to be in this final form. So again, here is that picture that's similar but not exactly the same. I want you to write that formula in that side of the picture. Okay. All right. Okay. That's it for our notes today, except I want you to go into Plan Book and watch these 2 videos. I'm not going to play them with you as we go through this, but the first one is of 3 minutes and something seconds. And this one is great at showing how that gas exchange is happening throughout the body and the entire system. And then the crash course video is a little bit longer, but I highly encourage you to watch that. He's going to talk about hyperventilation, which is going to be some questions on your homework assignment. And so I want you to watch the video so that you know how to answer those questions. I could talk about them right now, but he goes into what's happening with the carbon dioxide in your body. So make sure and watch this video so you can answer every single question on your homework assignment. That's it for Tuesday. We've got a few more notes on Wednesday. Thursday, I'll review. Friday will be your test. I miss you guys. Hope you're doing well. Have a great one.